are going to be learning about thermochemistry, chapter 6. And in this word, you should notice therm, heat, and chemistry. We're looking at the study of heat in chemistry. There are two key words that we're going to focus on, exothermic and endothermic. A couple things you should notice in these words. In exothermic, you should see X and therm. X like exiting, therm like heat. In an exothermic reaction, heat is exiting. Heat is a product. We sometimes say heat is given off. There's some other ways we could describe this. You have to get familiar with the language of the chemistry here. In endothermic, you should notice N like enter. Again, therm, heat. In an endothermic reaction, heat is a reactant. Sometimes we say heat is absorbed or used. Any of those words would suggest that we have an endothermic reaction. We have a symbol that we use for heat and a special word. We call heat enthalpy, and we use the symbol H for enthalpy. And in a reaction, we talk about delta. It's a Greek letter D, delta H. And whenever you see the delta, delta means the change in. Delta is also thought of as your final conditions minus your initial conditions. So when we're talking about a reaction, we would say that the heat of a reaction is the sum of the heats. Now, it's the heats of formation. The final conditions in a reaction would be the products, and the initial conditions in a reaction, what would the initial conditions be? What do you think? That's right, the reactants. So here we see the change in enthalpy. The change in enthalpy of the reaction is the final, sorry about that, is the final conditions minus the initial conditions. And heats of formation are found in an appendix in your book. The appendix starts on page 819 and goes through page 822. This again is where your heats of formation are, and I just realized when I was looking that up that we have a little knot here. It looks like a zero. It sort of is. Oops, I put the zero in the wrong place over there. It goes after the H, and that stands for standard conditions. For thermochemistry, standard conditions are 25 degrees Celsius and 1 atmosphere. This is not like gas laws. In the gas laws, the standard conditions are 0 Celsius and 1 atmosphere. The reason why we use standard conditions at 25 degrees Celsius for thermochemistry is because these heats of formation, the delta HFs, are actually measured quantities relative to pure elements at 25 degrees Celsius. And these experiments are done at 25 degrees Celsius. So human beings are conducting experiments. They don't want to conduct these experiments at 0 degrees Celsius because it would be too cold. Room temperature is about 22. It's easy to get to 25 degrees Celsius. Okay, so heats of formation, standard heats of formation values are measured values. They are defined as 0 for pure elements in their standard states at 25 degrees Celsius. We react pure elements with one another and find out how much heat is produced or used when the products are formed to find the heat of formation values for other compounds. And all of the heat of formation values are determined relative to pure elements. We'll learn later about entropy and Gibbs free energy. Entropy, it turns out, is not a relative scale, it's an absolute scale because there's a true 0. At 0 Kelvin, 0 Kelvin is the coldest temperature possible. At at 0 Kelvin, entropy is 0. Not relative, absolute. Gibbs free energy, again we'll learn about that later, is a relative scale just like heats of formation are a relative scale. And again, we will learn more about those later. All right, so if we look at an energy curve where the y-axis is energy and the x-axis is the reaction coordinate, we have reactants and products. We can look at this as, right here is the energy of the reactants, and over here we have the energy of the products, and we see the products have more energy than the reactants. The difference in energy between these two areas we would call delta H. It's actually the absolute value of delta H because distance has to be a positive value. So looking at this, we see that we have to add heat to the reactants to get all the way up to here. And if we're adding heat, that would be endo or exo. Hopefully you got the right answer. This would be an endothermic reaction because heat was being absorbed. We had to add energy or heat into the reactants to get to the amount of heat that the products have. If we were to look at an exothermic reaction, we would have the opposite. The reactants would have more energy than the products. Remember NRG for energy. RXN stands for reaction, and this is the reaction coordinate. Okay, so this would be an example of an exothermic reaction. Okay, so we can look at our reaction coordinate energy diagrams to figure out if we have an endo or exothermic reaction. We can also look at the value of delta H. If delta H is less than 0, the reaction, that's less than 0 is negative, the reaction is exothermic. Exothermic. If the heat of reaction is positive, greater than 0, hopefully you've got this figured out. What do you think? That's right, if you got it. The reaction would be endothermic if delta H was positive. So now it's time to do some actual problems and not just talk about this in qualitative terms. We're going to find the heat of reaction for the reaction that I have listed up on the board. What you would do, where would you go? That's right, appendix, page A19 through A22, and you would look up the heat of formation values for each of these different chemicals. So we look up the heat of formation for NH3, for O2, for NO2, and H2O. Okay, so you should pause for a moment and actually get your books out and look up these values and see how you find where these values come from. And you want to make sure you're looking in the enthalpy column, not the entropy or the Gibbs free energy columns. A19 to A22 in your book. One thing you might notice, important about this water right here, you'll see it's liquid water. Make sure you get the value for the liquid water and not gaseous water. The state of the chemical makes a difference. Gaseous water has a heat of formation of just negative 242 kilojoules per mole. So you do have to be careful and look at the physical state for each chemical. So now our heat of reaction is going to be products minus reactants. I have to multiply my coefficients, which represent moles, by my heats of formation for each piece. So it's my products. Here's my products. And we need to subtract our reactants. You have to be very careful with these, with your signs. The biggest mistake that students make is having incorrect signs or adding or subtracting incorrectly. That 46 joules looks really bad. I'm going to fix that. That was negative 46 kilojoules, not 46 joules. And you'll notice I was writing down all the moles because I want to make sure that I cancel appropriately. And then you want to, again, be very careful with your signs. You might want to put this in your calculator, see if you're doing it correctly. You'll notice over here you have a negative and a negative, which gives you a positive. Sometimes you have two or more reactants, and you have to make sure that you remember to subtract all of the reactants. And I could ask you, why did I ignore the oxygen over here? Why is this oxygen irrelevant? How did I know it was 0? I could have looked it up in the table. But you're going to have to remember all pure elements in their standard states, the standard heat of formation is 0. Okay, so what's the answer? And here we go, negative 1396 kilojoules. And don't forget, a joule is an energy unit. Kilojoule just means 1,000 joules. Nothing fancy, we've already learned. Metrics, K is kilo, it stands for 1,000. All right, now I've rewritten the reaction and we found our delta H. Now we're going to do stoichiometry with heat. Problems that involve stoichiometry and heat. So I could ask a question like the following. All right, I put two problems up on the board. They appeared out of nowhere. Isn't that magical? Sorry, just trying to make this a little more interesting and fun. When we have questions that involve mass and heat, and we have a reaction and we have delta H, we can use stoichiometry for a reaction, and the kilojoules in the reaction can relate to the moles of any particular chemical in the reaction to be used as a conversion factor. So for A, we would always start our ladder with whatever was given. We've got our 34 grams of NH3, and we always know it's grams to moles use molar mass. Grams, and we have to make sure we write the chemical, not just the units of grams or moles. And now we can use our chemical reaction to go from moles of NH3, 4 moles of NH3, to kilojoules. Now, let's look at the sign real quick. The question was, how much heat is released? The question is not, what is the change in delta H? If we are releasing heat, we are releasing positive heat. So I'm going to make this a positive 1396 kilojoules. If this question asked, what is the change in enthalpy for 34 grams reacting, then I would keep the sign here negative. However, because I asked how much heat is released, I need to keep this sign positive. Now, many of you would probably go ahead and take out your calculators and start calculating things, but you should notice this could be a calculator-free question. Let's simplify this. The 17 and the 34 leaves us with a 2. The 2 and the 4 leaves us with a 2. So our answer is just 1396 divided by 2, 6, 8, 8. Did I do that right? 6, 19, 8. Nope, this should be a 9. 18. Okay, we're good. So the answer would be 698 kilojoules. That is how much heat would be released if 34 grams of NH3 reacted. Now let's look at B. You've got 2792 kilojoules of heat produced. We're going to have to convert from kilojoules of heat to some kind of mole, and we're trying to get to moles of NO2. So we're going to look back at our reaction, and right here we have our negative 1396 kilojoules. But again, I'm going to use a positive 1396 because the question tells us that this amount of heat is produced. So it's positive heat being produced. We can use the absolute value of the enthalpy for the reaction. And according to the reaction, we would have 4 moles of NO2. And then we need to convert to grams. 1 mole of NO2. Oh, 16 times 2 is 32, plus 14 is 46 grams of NO2. Now, personally, I don't want to put this into a calculator the way I'm looking at it. However, I know that I made this question special. And if you pay close attention, first let's check our units. Forgot to do that in the last problem. Moles, moles, grams, grams. Okay. If we look carefully, and if I did this right, I'm pretty sure I did, you will see that these two cancel out to give you a 2 up here. So now I just have 8 times 46, which is 6 times 8 is 48. Carry the 4. 8 times 4 is 32, plus 4 is 36. 368 kilojoules. Now, I wrote these answers down, but let's check if I have the right number of sig figs in these problems. Let's see. In the first problem, notice, I have 2 sig figs. So my answer should actually only have 2 sig figs for part A. Oh, and I kept 4. So I need to rewrite this. I kept 3, sorry. I need to write this as 7.0 times 10 to the 2 kilojoules. That would be the correct answer for A with the correct number of sig figs. And for part B, notice I have 4 sig figs here. So in order to write this answer with 4 sig figs, I would need to write 368.0 kilojoules. Alrighty, there we go. So now you should be able to do problems with finding the heat of reaction given heats of formation, and also finding out how much heat is used or produced in a reaction given the number of grams that might have reacted, or to find out how many grams were formed or used if we know how much heat was used. Okay. At this point, you should be able to do, at the end of chapter 6, numbers 35 and 68. I think that's probably enough for now. There's some more practice you could do, but we'll do practice in class.